Okay, we're going to look at the geophysics of the flood. We've already defined, we're assuming we've already defined the flood rocks. What is it that we can learn about the geophysics of the flood? And the first thing I want to say is that geophysics is a science. Geo is referring to the earth. It's the physics of the earth. So the motion and activity of the earth. In opposition to something, or in contradistinction to something like the fossils of the flood or the sediments of the flood, the rocks of the flood. This is going to look at the dynamics of the flood. It is a science. As a science, we ought to begin with scripture on to determine what we can learn about that particular subject. Similar to other things that we have encountered in the flood account gives us very little to deal with, although it's better than fossils and better than rocks. There are some comments that may actually have geophysical significance. For example, in Genesis 7:11, it tells us that on the same day were all the fountains of the great deep broken up, and following that in the passage, it talks about the windows of heaven, and it talks about again, the fountains of the great deep. It's possible that the breakup of the fountains of the great deep has reference to the breakup of the crust of the earth, and that would be geophysics. There's actually a comment that may have great geophysical significance. You need to consider that. But the consequence, apparently, according to that verse, is that whatever that was, it resulted in a flood or a rising of sea level relative to the land, such that it went so far as to cover all the mountains of the earth for a sustained period of time. The whole flood event was something in excess of a year of time, and the effect of it, in context, the purpose of it, was actually to kill all humans and all land animals that were on the earth at the time, except those saved on the ark. And it's that particular account of the flood that we're interested in considering. Again, there's a little bit that we can possibly deduce from that passage, but most of what we're going to have to learn from flood geophysics is going to have to be from the world. Looking at the rocks we think are formed in the flood, inferring the nature of things from those rocks. And I'm going to begin with... there's a lot of different places I could begin. I'm going to begin with what I call megaquakes, big earthquakes. Because in the flood rocks, once we've defined the rocks we believe to be the flood rocks, which are what the conventional world would call the Paleozoic and Mesozoic rocks, we have evidence of megaquakes, big earthquakes. I mean big earthquakes. And so I wanted to address a little bit of how I even know that there are such things as big earthquakes. Let's say you've got some water carrying sand, and it drops out the sand into a layer of sand. If you looked carefully at it, microscopically at the sand, you recognize the sand grains are deposited in what you might call a random fashion. There's often pockets in between the sand grains that still contain water. The sand isn't as close packed as the sand could possibly be. Under almost no circumstances do you actually drop sand down in water in a close packed fashion. So there's extra space in here with water in between the grains. If that particular sediment is hit with a significant shock wave of some sort, jostled, if it is shaken, the individual particles, sand particles, will in fact go into a close packed pattern, or at least approach it, move in that direction. In order to do so, though, it's got to push the water out from in between the sand grains. And typically then the water would go upwards into the sediment above. If there's already, for example, layering in that sediment, that water that's rising in the sand will deform the layering that already exists in the sediment. And the deformation of these what were formerly, let's say, horizontal structures, the deformation results in what we call fluid evulsion structures. It exhibits itself after earthquakes, for example. One example of a shock wave running through sediment would be an earthquake wave running through sediment. If it's, and here's an example from the Loma Prieta earthquake, Richter 6.9 on the Richter scale, in the midst of a field. It's shaken up the sand in the soil underneath the surface. It's caused water to rise up to the surface. That water carries with it even sand grains from beneath and creates little sand volcanoes, depositing sand on the surface. It's really strange if you're involved in an earthquake and see this. Is pretty cool. Well, geologists think it's pretty cool. It's really fun to watch the well, you might be standing on a sidewalk, for example. Some great photos from a New Zealand earthquake taken from a person's on a sidewalk, and it's a little jiggly, but you can actually see these sand volcanoes produced right beside the sidewalk and pile over the sidewalk as the person is watching this. With significant, if there's a very significant earthquake releasing a tremendous amount of water into sediments above that which have been settled down, if there's enough water mixed with the sand, you create effectively a quicksand situation. You liquefy, what we call in geology, the liquefaction of the sand. And if anything's on top of that sand, like let's say you've got a car sitting on top of that sand, all of a sudden the car sinks in like it's sinking into water because there's so much water relative to the sand being evulsed from the material underneath into sand that it causes the car to collapse beneath the surface. It can also take out the foundations of houses or buildings, large buildings that have been built upon the sand. Bad idea. We get that idea from the scripture, don't we? You aren't supposed to do that, but people still do it because it's much cheaper than digging all the way down to bedrock. But if you do set your foundation upon sand and an earthquake comes along which liquefies that sand from material underneath, the building just dips in just like the car does, and you end up with buildings falling over. Very strange, but amazing stuff. Now, the other thing is that you can see these kinds of things in sediments. That what I was talking about is things you could see at the surface, but let's say after the earthquake has come along, you went and cut down through the sediment, looking at those formerly horizontal lines that are now evulsed you will see that in cross-section. And here's an example in some Dead Sea muds. Normally flat-lying, alternating light and dark muds that an earthquake has hit at this particular point up. Well, it's actually throughout this. This is a 3-inch section of the muds formerly before the earthquake disrupted them. It's probably looking very much like this. But water is evulsed from these sediments and deforming them and creating some really interesting structures. These are things observed by Steve Austin in his study of muds around the Dead Sea. In this particular situation, he identified that particular layer as this one here and identifies it with the 31 BC eruption that we're familiar with. Counting, actually, and redating, there's another layer here that was only 3 inches thick and can't really be seen in this photograph. The deformation can't be seen at the scale, but here's one here where the deformation actually shows up, and it's about 6 inches of deformation in mud. So you got, rather than 3 inches, you got 6 inches. So you've just about doubled your deformation. We know that this earthquake is associated with an earthquake in 750 BC. We have a rough estimate of the Richter power of each earthquake based upon We don't have, obviously, a direct measure of this. It's inferred from a variety of sources. The bigger one is, in fact, the one with bigger deformation is a more powerful earthquake. It's about 16 times the power of the smaller earthquake, and it results in just doubling the height or the amplitude of the deformation. So we can look at sediments based upon this kind of information from earthquakes we're familiar with, and the biggest earthquakes that we've seen in the present, the 1964 earthquake, the largest one in North America in recorded history, in recorded history since we've had seismometers, produced 11 inches of deformation. It was a big earthquake, 8.4 on the Richter scales, bigger than, it's again another probably 16 times more powerful than this earthquake, and it again approximately doubled the deformation. So we can look at ancient sediments. We can see deformation that matches the kind of deformation we see in modern earthquakes, and that deformation we would assign a name to. That's a seismite. It's a sedimentary structure produced by seismic activity, by an earthquake. So that's a seismite right there. This is another seismite right here. We should be able to identify seismites in the record. Plus, if we know from the present what kind of power is necessary to produce a given size of deformation, we can use that to estimate the power of ancient earthquakes. So when you find deformation structures that are of this size, and my scale here is sitting in the back. Jeff is nearly 6 foot. What are you? 6'1". Okay, 6 foot 1 inch tall. Here's a deformation of a sandstone unit that is 1, 2, 3, 4 times his size. It's 24 feet thick. Okay, if the biggest earthquake in recent history, since we've had seismometers, produces 11 inches, and to double this puppy, you've got to increase the earthquake power 16 times. What kind of power is involved in this? This is a monster earthquake. And there are bigger ones, okay? We encountered 30 foot, 35, even 40 foot layers, 40 feet of deformation. These are monster earthquakes, but they're the smaller earthquakes at the end of the flood. There are bigger ones in the flood itself. If you look at, there's an aerial photo looking at a portion of the Grand Canyon. There's a structure along here which is actually an earthquake fault, and we can see, if you go into this canyon and take a look at the wall of the canyon there, with the fault being off just out of view in this image, we're looking at layers of rock sitting over here that are doing certain things before they get to the fault, and they've been deformed by the fault. Now, for scale, there's some humans here. You can't see them hardly, but this is a pretty big structure. If you follow this particular unit, which is the Tapete sandstone, for hundreds of miles, it's pretty much as flat as can be. It's normally a flat-lying unit. It's only deformed here in response to the fault, in response to movement along the fault. We know that this deposit was deposited probably very soon at the beginning of the flood, probably on the first day of the flood or so. It's deformed at the end of the flood. So 1 year later, it's deformed, and it isn't just bent upwards. If you actually trace the rocks, it's recumbent folded at least 3 times, and it's hard to trace some of these particular layers sometimes. We have an incredible deformation that is occurring, and the motion along the fault is indicative of at least 1 mile of motion. So probably it may have been in a single earthquake that actually had 1 mile of motion along this fault. If it wasn't a single earthquake, it was a series of earthquakes over a very short period of time, certainly within months, but probably within days at the most. And this is again just mind-boggling to think of. The 2004 tsunami that killed 250 million people was caused by an earthquake that moved rocks along a 1,000-mile long fault 60 meters. It just moved it 200 feet. That's it. This is in excess of 1 mile, and the fault is much longer than 1,000 miles. This is a very big fault as well. So this is a monster earthquake. There are bigger ones than that, because again, that earthquake is at the end of the flood, probably at the low end of the power of the flood. Everything I've shown you is the little stuff at the end of the flood. Here we're getting further down in the flood. This is a cross-section of a carbonate where it's hard to see, I understand, but the carbonate has been broken apart into pieces. It's been what we call brecciated. So carbonate is something that once it forms, it starts out a lime mud, which is really gooey, but it sets into an extremely brittle rock. Very difficult to bend, basically impossible to bend, so it tends to fracture if it's forced to bend. And if there's sufficient power given to it, it fractures into a breccia, into breaking into sharp pieces. And this is an example of a carbonate unit in the United States that has been brecciated. In fact, there's a series of these carbonate units moving from the southeastern United States across towards the northwestern United States. There's a series of individual limestone units that are brecciated. And if you look at them in that geographic sequence, they don't all date at the same time. They have different radiometric dates that indicate that the brecciation started in the southeastern United States and moved across the continent as whatever it is that brecciated these things moved across the continent, brecciating the dolomites and limestones in that sequence. If you follow the evolutionary scenario, the old age scenario, it crossed the continent in 100 million years. There was some sort of deformational wave that went across the continent from southeastern U.S. to northwestern U.S., that the wave deformed shale fairly easily. Shale could be bent and bent back with no trouble, but when it hit the limestone units, it brecciated them. But it took 100 million years in radiometric time for this wave to cross the continent. That's the conventional explanation for this. I would say that's absurd. We know of no such deformation that can move so slowly. Anything with an impulse and a relative motion of that magnitude is going to move through rock at about the speed of sound. It's going to move at 534 feet per second or whatever it is through that rock. We know of nothing that can deform rocks so slowly but powerfully. What is that? So if you actually connect these rocks as they do genetically in the conventional literature and put a proper speed on this puppy, this is a seismic wave that crossed the continent of such magnitude that it took 1 foot, 2 foot thick limestone units and just scrambled them. as it went through, which would, I would suspect, if you were standing on the ground, it would break every bone in your body. It would move things up so quickly that you would be hitting the ground, and the ground would be hitting you, and it would just smash all the bones, and it would be a horrible mess. But this is a monster earthquake. That's bigger. It's not just bigger than anything we have in the present. This is not even conceivable. Now here's another one that is a little older than that, the beginning of the flood, that I think is the biggest earthquake in the Earth history. We go out to the Kingston Range in California. There is the Kingston Peak is the highest peak in that range, and there is a formation of rock named after Kingston Peak found in the Kingston Range called the Kingston Peak Formation. That rock is a diamictite by description. It's a rock made of two different sized rock particles, mostly sand, but mixed in the sand are these rock fragments. Some of them round, some of them angular, thus breccia. It is this particular, and it's called thus a diamictite. That particular unit has some pretty big boulders in it. This is a boulder that is 1/4 mile in diameter. It's hard to see these. I mean, no matter how I did this, we took photographs from the plane. We took, it's impossible to see from the ground. There's not much of a difference in color contrast between the matrix and these boulders, but here's a boulder here, here's a boulder here, here's a boulder here, another one there, another one there, another one here. Each of these boulders is approximately 1 mile in diameter, about 200 meters thick, kind of like dinner plate shaped things, 200 meters in thickness, and several of them are actually imbricated. They're stacked on top of one another in this diamictite. These are monster boulders. I worked in this particular unit for 10 field seasons before I had to abandon the project. Towards the end of the project, I was beginning to believe that there's actually much bigger. I had only seen things that were 1 mile in size, but I believe there's 3 to 5 mile diameter boulders in the same unit that I started out thinking were the bedrock that hadn't been moving, but I began to realize, wait a minute, these aren't actually bedrock pieces, these are boulders inside this deposit. We inferred, in order to explain this, is actually the evidence indicates that this is an avalanche deposit. It's in excess of 1 mile thick, probably closer to 3 to 5 miles thick. So it's a let's say a 2.5 mile thick avalanche deposit. The evidence is that it fell more than 1 kilometer because it exploded boulders that you can only do if you drop the rock that far. And so we have to have something that could take that much rock and drop it down at least 1/4 mile. There's evidence it was formed underwater. And so we believe that it's actually due to the collapse, an earthquake that collapsed the edge of the continent. And this is an avalanche that came off the continent. You've got the difference between the continental height and the ocean depth is currently about 4 kilometers. So you've got plenty of vertical to explain that. And on this map that is our best reconstruction of what the continents look like at the time this particular rock was formed is located right here. It turns out that in the same aged rocks all around the world, we find the same avalanche deposits scattered all the way through, right through the middle of Australia. This is Laurentia, which is North America, but right through the middle of Australia, what is now Australia, right through the middle of South China, around the world, at what is, when you put the pieces back together, the edge of the continent all around the world at the time that this was made. So there appears to be, and radiometrically, they are dating at identical ages. They are the same age stuff. So this is all occurring at the same time. So we're collapsing the continental margins of the entire world by an earthquake. It's probably an earthquake that cracked along a fault, probably along the edge of the continent at the speed of sound. So it's probably an earthquake that took 4 to 5 hours to actually occur. It cracks along the fault, kind of like unzipping a zipper or something like that, just as the 2004 earthquake actually was that 60-meter motion along 1,000 miles. It actually moved along the fault, cracking the fault along the way. And so rather than a really big earthquake taking about 20 seconds, this would have been an earthquake that took 4 to 5 hours. And in the process broke the continental edges around the entire, all the continents of the world. That's a monster earthquake. I think the biggest earthquake of Earth history. Those are all part of the flood. That's part of the geophysics of the flood. What's the cause? I mean, these are monster earthquakes. What causes those things? That's geophysics, but what is it that gives the power to the earthquakes? And that's what I want to address. So in what we've looked at, I'm trying to think here. This is not, I don't think this is the right presentation. Okay. Anyway, we've looked at megaseismites, those big things where Jeff is the scale for. That's the end of the flood, the little guys. Brecciating crustal waves moving through North America, brecciating the rocks of the continent. That's earlier in the flood. The global collapse of the continental margins at the beginning of the flood. We're probably looking at sort of the pattern is decreasing power through the flood, but awesome, unbelievable power throughout. And what is causing it? My suspicion is plate tectonics is the cause of this. Now, conventional plate tectonics is an amazing theory in geology that explains an awful lot of features on the present world. It explains the shapes of the continents. It explains geology on opposite sides of the ocean without that matching geology in the oceans. It explains the position of volcanoes and the chemistry of volcanoes, the location of earthquakes and the nature of earthquakes. It's a wealth of things that are explained by plate tectonics. It's a very powerful theory to explain a lot, but it does have a few problems. Biblically, it's moving continents at centimeters per year, which is the rate at which your fingernail grows, much too slow to be accommodated in the midst of a global flood. But there's other problems. We can actually measure the continental motion, actually measure current continental motion with satellites. Satellites can look at North America and Europe at the same time and can measure the relative motion between the two. And although the motion is very often within that range of centimeters per year, in many cases the motion's going in the opposite direction as it's supposed to go, and in some cases it's not moving at all. It's a really weird mixture of the direction doesn't make sense, the magnitude average is about right, but something's wrong with the motions. Also, the trenches, which are places where subduction is occurring, and where that occurs, if there's debris here in between the continent and where the plate's going down, it's going to mess that stuff up. But all the modern trenches are full of sediment that's undeformed, as if there is no subduction in those areas. That's just bizarre. We've also got some other things that are interesting. We've got minerals inside mountain chains that are the result of collision between continents, but the minerals in those mountain chains include high-pressure, low-temperature minerals. These are minerals that are formed under extremely high pressure, which makes sense if you bury these things very deeply. They would be buried under a lot of rock and thus be in a high pressure. But if you do that slowly, the way plate tectonics suggests, they'll also heat up to the temperature of the Earth at that depth. And so you can't have high pressure, low temperature minerals. You would have high pressure, high temperature minerals. So how do you explain high pressure, low temperature minerals? And then there's things like diamonds. You all love diamonds, right? I mean, diamonds are found in a rock called kimberlite. Kimberlite is this wild rock that, I mean, that's the best way to describe it. It's a wild rock. Let's back up a little bit. We know from making diamonds in the industry, we know exactly how diamonds are formed. We can make them. We know precisely the composition. We know the temperatures and the pressures. You got to have a certain high temperature. It's sort of equivalent to about 10 kilometers of rock piled on top of you. That's how much pressure you have to have. And you have to have the right chemistry, basically pure carbon. And once you've done that, now there's one other ingredient to the recipe of making a diamond. You've got to quench it just right. The issue is you've got to take it out of that environment. It's under all of that pressure at those high temperatures, and you've got to bring it to atmospheric pressure and temperature in between 5 and 10 hours after you put it at the right temperature and pressure to start with. If you take too long, it simply converts into graphite, and you have nothing worth a diamond. If you do it too fast, it's like throwing hot glass into water. It shatters, and you have tiny, tiny pieces that you can't do anything with. So there's a very precise range here. You got to take it from what, 10 kilometers beneath the surface to the surface in 5 to 10 hours. You can't do it slower, can't do it faster, or you don't get diamonds. So how do we get diamonds? Yeah, in conventional plate tectonics, things move much too slowly to get things up to the surface in such a time. So these and several other things suggest, as amazing as plate tectonics is, something's not quite right. And the rest of the answer is basically the bottom line is speed up plate tectonics about 3 billion times and you got it. Okay, that turns out to be the answer, we think. We got a group of scientists together back in the late 1980s and early 1990s. I heard a talk by Russ Humphreys and a talk by John Baumgartner, and I thought, whoa, these puppies can be put together. And so I was rooming with Steve Austin at that conference. I sat down with Steve and I said, we got to talk with John and Russ, and we ought to be able to put together, I think we can put together a flood model. We got together, we added in time Andrew Snelling and Larry Vardaman. And the reason we did this is because John Baumgartner is a physicist, Russ Humphreys is a physicist. These guys have their heads in the clouds. They know nothing about reality. They create, John was creating imaginary models. You got to make sure that it corresponds with real rocks. So you need to combine these with people who, rock heads, people that got rocks in their heads. Steve is a soft rock geologist. Andrew is a hard rock geologist, and I'm a paleontologist. So the idea is, let's bring these physicists in out of the clouds. Let's connect them with real world. There were times when John would say, this is what's going to happen, and he'd go, no, you just evaporated all the critters on the planet. I'm holding out for the, You can't do that. You won't have any fossils, so you got to ease it back a little bit. And there were times when Andrew would say, "Oh, wait a minute, that isn't what the volcanic sediments would indicate," and so on. We added Larry Vardaman working on the atmospheric physics. John basically worked on the mantle of the Earth. Russ was modeling the core, the outer core of the Earth, and Larry the surface of the Earth. So when you put the 6 of us together, it isn't everything. It doesn't cover the whole spectrum, but it covers most of the fields of geology and physics that would be necessary to put together a flood model. It wasn't just a random group. It wasn't just a group interested in the project. We specifically put together people who were capable, who could potentially at least be capable of creating such a model. And ultimately, the model looks very similar to a proposal made in the 19th century by Anthony Snyder, a person who had an idea about the origin of the Earth but couldn't get his publication published in the United States. He ultimately only got it published in France, La Création et de ses mystères dévoilés, The Creation and Its Unveiled Mysteries, is the title of his publication. And in his publication, he actually draws out, this is 1859, it's amazing, he draws the continents in a position that might be all familiar to all of you, the Pangea reconstruction of continents with South America tucked into Africa, North America into Europe, and so on. But this is unheard of in the 19th century. This is crazy. And in the course of his book, he says that these things separated to the present, these are illustrations from his book, in the flood. So he's suggesting that somehow in a single year, the continents moved apart from the pre-flood configuration, which was what he suggests was the case over here, to the modern formation. And this basically, this kind of summarizes our model. We're moving things around on the surface of the Earth, plates on the Earth, about 3 billion times faster than the conventional model says it actually did occur. In our model, we start with an Earth that is very much like, in large part, very much like the way it is now. The current Earth has a core mantle and crust. The inner core of the Earth is presumed to be a solid iron-nickel core. We know the composition because of the total mass of the Earth, which we can calculate because of its gravitational effects on other things. So we know its total mass. We know the type of material that's out here in the outer portion of the Earth. But if you project that material all the way to the center, the Earth ain't heavy enough. So you've got to put stuff in the center of the Earth that is much more dense. And based upon meteorites that have a set of compositions, one set of compositions that is iron-nickel, another set of composition that is similar to the mantle of the Earth, and another set that's similar to the composition of the crust of the Earth. And approximately 80% of the meteorites have a mantle composition, approximately 20% have an iron-nickel composition, and a very, very small, almost insignificant percentage of them have a composition similar to the crust of the Earth. We then project that iron-nickel composition onto the center of the Earth, and it gives us and we know the size of this from seismic waves, it gives us the right mass, total mass for the Earth. So we presume that there's an iron-nickel inner core and outer core. We separate these two because earthquake waves going through this, certain types of earthquake waves go through both cores without any trouble whatsoever. Compressional waves, waves that move the material forward and back, can go right through the outer and inner core with no difficulty. But transverse waves, waves that move material laterally and thus rely on shear forces, do not go through the outer core, which suggests that the outer core is in fact liquid. And we estimate its viscosity to be similar to the viscosity of water. So it's a very thin liquid, but it's iron-nickel. But then there are compressional waves that go through the outer core, get transferred into transverse waves through the inner core and back to compressional waves through the outer core. So we know, and it's complicated, but because each time it deflects the pattern a little bit, we know from the shadow of waves on the other side that there's an inner core that's actually solid in the midst of that liquid core. That's about half of the radius of the Earth, but collectively only 20% of the total volume of the Earth is occupied by the core. 80% of the volume of the Earth is mantle. With a different composition, it's a silicate mineral that dominates in the mantle. It is a mineral that at the pressures and temperatures that would be indicated here, the mantle can behave somewhat plastically. It's not brittle. It's not, it can be deformed in ways that the crust cannot be. And the crust, I don't even show the crust on here because the thinness of the crust compared to the rest of the Earth, it wouldn't show up. It's so thin. The crust is just a scum on the outside of the Earth that we are very thankful exists. Because if the scum weren't there, we would be boiled alive and all that sort of thing. But it is just almost at this scale, it's something you could ignore. But that crust is in two types on the surface of the Earth. There is something we call continental crust because it underlies most of the continents that we have today. There's another type of crust known as we call oceanic crust because it underlies most of the oceans. The oceanic crust is 5 to 8 kilometers thick. The continental crust is about 35 kilometers thick. In places, like underneath the Himalayas, it gets up to 70 kilometers thick, but usually on the average it's about 35 kilometers thick. So much thicker than the oceanic crust. But the difference between these two is in the composition. The oceanic crust has a density greater than that of the continental crust. Because of the greater density, it sinks, it floats lower on the mantle. Like a denser wood would float deeper in water than a lighter wood would float in the water. So because the density of continental crust is less than the density of the oceanic crust, we have, if you ignored the water on the Earth, you would have these deep basins where the oceanic crust was, and there would be highlands where the continents are. But we have oceans that fill most of the basins, and that's why we have oceans where we have them. It's caused by this relative density of continental and oceanic crust. So here you can see, by the way, and I throw this in, this is polar view, but these shallow areas of ocean, shown up by light blue, are all part of the continental crust. Geologists look at continents being a little bigger than the shoreline. You follow them out to a break, to an edge, which is only 135 meters below sea level. At that break, it then drops off into an ocean that is 4.5 kilometers deep on the average. So there's quite a break, quite a drop off there into deep ocean. In our model, what in fact initiates the flood? We've got this verse that says, "The same day were all the fountains of the great deep broken up and the windows of heaven were opened." It suggests perhaps that the crust of the Earth, the surface of the Earth, was broken in some way. This is what we think was the case just before the flood began. Not only was the oceanic crust denser than the continental crust, but we believe the oceanic crust was a little different than the present oceanic crust in that it was colder. Let's say it was normal temperature. A lot of our current oceanic crust is actually kind of warm. Having been actually recently produced, it is still warm from having been made from the hot material, the mantle. But we presume that at the end, just as the flood began, all the ocean crust was cold. Now what's interesting about the present oceanic crust, where it is cold, the oceanic crust is actually denser than the mantle underneath it. So if we presume that that was the case for the pre-flood condition, that would mean the entire ocean crust was actually denser than the material underneath it. That's an unstable condition. We suspect that wasn't the condition from the beginning. We suspect that probably something happened at the fall that created that inversion of density, that the upper mantle was stronger in the pre-fall world, and that maybe it was the buildup of heat from radioactive decay between the fall and the flood. We don't know, but we suspect that in the original creation of the world, there was not this unstable condition. But at the beginning of the flood, we basically had 70% perhaps of the Earth's surface was floating on top of stuff less dense. There's denser material floating atop less dense material. If you just, and you can do that, you can take a sheet of aluminum and put it on water if you're really careful. Now, as soon as you let the edge of that aluminum slide under the water, man, that puppy goes down. But you can maintain that condition for some time, and we suspect that that was the condition just at the beginning of the flood. What then dipped the tip of the crust into the earth? What started it all? We don't know. The answer is unknown. Could it be a terrestrial cause? Could it be, again, could it be buildup of radiometric heat energy that kept increasing that difference in density to where it just couldn't handle it anymore and just collapsed? Could it be that something came in from the outside and pushed the edge down someplace, or pushed the middle down someplace? Could it be a meteor that hit it, or a comet that hit it? These are things that we don't know. Could it be, and John Baumgartner suggested somewhat tongue-in-cheek when it was originally suggested, but we always thought it was kind of funny. When he suggested it, he was, and I think he was serious. I don't know. We weren't sure if he was tongue-in-cheek or not, but he said he thought it was so close to breaking on its own that it was God slamming the door of the ark that was the last straw that caused the whole thing to occur. I kind of like, I mean, it's aesthetically pleasing. I kind of like that idea. It may not be true. And the other could be just, finger of God. He just said, okay, that's enough. And that's all she wrote. I don't know. So we just don't know about that. We still don't know about that. But what happened in our model is that three things occurred simultaneously. And I can't hardly talk about one thing at a time, so I can't talk about three things at a time. But these three things, subduction, mantle-wide flow, and yeah, right, the rising, are all have to happen at the same time. I'm gonna speak of them in sequence. In sequence of three, but you have to keep in mind that they're all simultaneous. And this is the first one I'm going to talk about is subduction. And what subduction is the idea that the ocean crust began diving into that mantle. The ocean crust, which was denser than the mantle, had that opportunity to dive in. Once it did, it did. And that's called subduction. Now, the model at this point is based upon John Baumgartner's modeling of the interior of the Earth. What John did for his PhD dissertation is he modeled the mantle of the Earth with basically a finite element analysis modeling, which we use to, you can only do so many experiments with materials, but you can create computer models that simulate those materials, at least if you describe the materials properly and put the proper information into the computer and build a bridge with it, you can put stresses on the bridge in the computer program and see if the bridge holds up. Rather than build an experimental bridge and then see if it holds up, if you did this right, you could actually design a bridge before you built it, that would actually stand up. That's the idea of finite element analysis in materials science. And he was wanting to do that same sort of thing to the mantle of the Earth. Now, what he's going to do here is plate tectonics had already proposed that what was happening was that plates sank into the mantle, and that the mantle moved out of the way in a circular fashion, creating a circular motion in the mantle, or a flattened circle motion in the mantle. And this sort of motion, simple motion, that can be seen, by the way, if you put a pan of water on the stove and turn on the heat, you can begin to see the water circulate in that pan. That's what we're talking about. The mantle is circulating in that fashion. That was modeled two-dimensionally. You can take a two-dimensional cross-section, and the mathematics for modeling that is fairly easy. But John was wanting to model this three-dimensionally on a spherical Earth. Okay, and that hadn't been done. No one had ever, that was a lot of mathematics, and in fact, it couldn't be done without supercomputers. And so he was kind of early on in the revolution of supercomputers that he could model the Earth three-dimensionally, the mantle of the Earth three-dimensionally. So the idea was to divide the mantle into a bunch of little boxes. And here is the, he divides the mantle first into these shapes, and then this smaller and smaller and smaller and smaller. And so he's got, gets to a point where ultimately he's divided the mantle into something in excess, at this point, an early version of his model, something in excess of 100,000 little boxes. So now what he does, so the idea, once he's done that, now later versions he would get more, you could make your pixels smaller by making more boxes, but of course it's harder on the computer, takes longer on the computer, crashes your computer earlier. But early on, his early model was approximately 100,000 boxes. In each box, he has the computer solve a few simple partial differential equations. These four equations are, three equations, sorry. These three equations are real simple equations. As you can see, the basic idea is very simple. Here's your box. What comes in has got to come out. And that means what temperature, what heat comes in has got to go out. What momentum comes in, linear momentum comes in, it's got to come out. What rotational momentum comes in, it's got to come out. It's more or less as simple as that. It's basically saying once you've divided your whole mantle up into all these pieces, you're studying the motions in the mantle, and you just can't keep packing matter into this little box. The matter going in has got to come out somewhere. So he's got to do this in each box simultaneously over the entire mantle in 100,000 boxes all at the same time. This is where it becomes, impossible for the human mind or a simple mathematics. It's where you need the supercomputer to do the project. And here's an example of a supercomputer that he used relatively early on. He first had Cray computers as they were being developed. Then he got to where he used this particular computer in Japan. I mean, this is in a day when we're making computers out of our watches, this sort of thing. We still have computers on this planet that fill rooms. They are monstrously fast computers, of course, you could imagine. But these are the kinds of things he was using. Now, keep in mind, and this is important to understand, his computer model is so complex, is so difficult, that it crashed the world's fastest computers in only, he could only simulate 60 days of real time. And so he crashes the computers in a half hour in every case. And now, it's been a long time since he started this in the 80s. We've gotten faster computers, but he's a software, he's creating software. He wants things to get better and better, right? So about the time they come up with a faster computer, he's put more boxes in there. So over time, He continues to crash the world's fastest computers in a half hour, and he's never broken the 60-day boundary. He can't simulate more than 60 days of time, which out of a 360-day year isn't bad. 17% of the, but it's not the whole flood, okay? We're only, this is just the beginning of the story, or maybe the middle of the story. It's just a little part of the story, but gives us hints as to what might actually have occurred in the course of the flood. And basically what happens here in the model is the crust. So he's going to represent, this is a two-dimensional picture of cross-section of the mantle. He's doing it in 3 dimensions, but you can't see that, you know. So we're just going to take a two-dimensional cut through the mantle. So this is the base of the mantle. Core would be down here. The crust is up there at the top. The red represents the initial temperature of the mantle at various places. So the red down here is not the same temperature as the red up there. The red down here is the temperature of the base of the mantle normally at the beginning of the simulation. The red up there is the temperature of the mantle at the beginning of the simulation. In other words, here it's close to 0 degrees centigrade. Down here, about 1400 degrees centigrade. Here it's about 3000 degrees centigrade. So, but this is, the red represents the initial temperature. And now what he does is he has a slab on the surface dip down into the mantle. He's going to see what happens to the slab. Here's a slab being represented. It's cold relative to the temperature of the mantle. As it goes down into the mantle, it's got to displace the mantle. You have arrows indicating how the mantle is moving in order for the stuff to go down into the mantle. As it does so, the mantle moves along the side, or the plate slides through the mantle. There is frictional heat that is built up along the sides of the plate. Also, as the plate drops down, and early on, this is a pretty big resolution. It's about 200 kilometers, which is much bigger than the plate really is, but that's the resolution he had initially. It's going to move the mantle material away as it dips down. It deforms the mantle. If you take a rubber ball and squeeze it and deform it, it'll warm up. So deformation of the mantle also heats the mantle. It heats both the mantle and the dropping slab. And the key here, though, is that the material of the mantle and the material of the slab, the viscosity of the mantle is related to is inversely proportional to the temperature to the 4th power. That's really cool. Yeah, you didn't understand. What that means is if you double the temperature, it drops the viscosity to 1/16 the viscosity it had before. So the more you heat it up, the more runny the mantle gets. So as the slab goes into the mantle and heats up the mantle around it and deforms the mantle, thus also heating the mantle immediately around the slab gets runnier, which causes the slab to increase its speed. Increasing its speed heats it up even more, it accelerates. So in his model, the slab accelerates up to about 1 meter per second, or several meters per second. Unlike conventional plate tectonics suggested, where it's only moving at centimeters per year, his slabs are sinking at meters per second. And so rather than continents moving at the rate your fingernails grow, they're moving about as fast as you can run. This is not continental drift, this is continental sprint. Because attached to the other end of that slab that's being pulled into the mantle by its own buoyancy is a continent that's pulled along the surface as fast as the other end of the slab is being pulled into the mantle. And so it stretches and it heats up. You can see the heating in the colors here. And looking at now a cross-section across the entire mantle, some 20 or 30 days into his simulation. He's got, again, now here, these various illustrations by John, he kept changing colors, so it's going to be confusing. But in this particular case, green is the original color, is the original temperature. So, and it's kind of nice because green's in the middle, right? So anything that is going towards the red is increasing the temperature. Anything that goes towards the blue is decreasing the temperature. In other words, sometime after the simulation, it went from green to blue. This area cooled. This area heated up. And so what we see developing, and then we got arrows to indicate motion. Here is a slab that's moving along the surface and diving into the mantle. Because the slab is cooler, it is showing up as a cooling of the mantle. But notice there's some other things that come in. This is the subduction. I can't point out the other stuff yet. This is where the subduction is occurring, and it's occurring over here on the opposite side of the world. Subduction is cooling the mantle. There it's showing up on a simulation. Two places on opposite sides of the world where subduction is occurring. After playing around with a number of continental configurations, John settled on this continental configuration to start with, and I know this is confusing. There is a thin dark line around the current positions of the continents. So right here is South America, North America, current positions, Africa, current position, Asia, current position, Australia, Antarctica. But we know from the geologic column, there was a time when the continents were together, called the Pangea configuration, and he's starting with a Pangea configuration. So he's got South America tucked up against Africa. India is tucked in there with Antarctica here and Australia here. North America is tucked against Africa and Europe, and that's the Pangea configuration. What John did is had subduction go along the blue here. This is where subduction is occurring in his model. When he allows subduction to occur in those particular places, what happens is that in time, the continents move apart from one another as we think they did based upon geological data. This is really cool, okay? No one had ever created any sort of model that moved the continents in the right direction. Let's take a look at this. Here we have 15 days into the flood, since the beginning of the simulation. North America has split away from Africa, and it's heating up there between the two because hot material from the mantle is coming up. That's another part of the story. It's occurring at the same time. Here are the direction arrows for North America. Here's the current position of North America. Here's the position in the simulation. The arrows are heading in the right direction. They're heading right straight towards the current position of North America. That's cool. Okay. You've got here's Australia over here in its current position. Here it is in the simulation. Here's the direction the arrows are going, right straight towards the current position of Australia. This is cool. Here is Antarctica. I mean, this was so exciting to everyone. Secular, everybody this was just mind-blowing. Here's Antarctica. Here's present position of Antarctica. Arrows are going straight south. That's where Antarctica is, right? This is cool. Everything is going just exactly the direction. One little interesting comparison. Here's South America. Here's the current position of South America. Position here, the arrows are going this way. That seems to be the one thing that's not going in the right direction. But alas, if you know geology, you get really excited because we know from geology that the last motion of South America was straight to the north to slam into North America and close the Panama Canal and close the central. So the real direction South America took was to go south and then swing to the north. And here we have the southern motion at the yes. And if that wasn't exciting enough, this is what John picked up. John picked that stuff up, and he was excited about it. Everybody's excited about it. But what got me, and I got really excited about, is as the simulation progresses, the length of the arrow indicates the speed. So little arrows indicate things that are moving slowly. Long arrows indicate things that are moving more rapidly. As this progresses, India gets really long arrows. Out of all of them, it almost doubles all the other arrows. And I looked at that and said, that's incredible. We know that India moved faster than every other continent. And so it didn't just move them in the right, and it slams into southern Asia and raises the Himalayan mountains. I mean, it's spectacular stuff. It didn't just move the continents in the right direction. It moved them with the right relative velocities. Mind-bogglingly amazing. This is cool. Okay, this is 15 days into the flood, 20 days into the flood. 20 days, it's moved this far apart. Now, what's also cool about this period of time when John is actually publishing this in the secular literature is he would publish these diagrams, black and white, they weren't as pretty as this, in the technical publications. Off to the side over here, and I blocked it out because it's all messy. You've got all sorts of information there, lots of numbers, and included there was the time, colon. It would be, in this case, 2.5 times 10 to the first days into the simulation. I mean, it's right there. And it's in the publication. It tells you how long it's been since the beginning of the simulation. It would be published in the article with this caption underneath it, with this stuff all here. It says, here's the position of the continents 25 million years after the separation began. I mean, if you look carefully at the publication, it's right there. You can't do this slowly. It doesn't work slowly. It stops completely. Boom. It don't go nowhere. I mean, it accelerates into speed, or it doesn't do anything. And so it was exciting to the world, but they had to modify it just a little bit, like slow it down a lot, 3 billion times to make it work. Here, the opening of the Atlantic is seen here in the Arctic, the opening of the Arctic Ocean. Here you see Australia moving away from Antarctica, Antarctica swinging to the current southern position. Amazing, cool stuff, but that wasn't the only part that was cool. Here is his simulation. What he's doing here is he's looking inside the mantle, taking a sphere inside the mantle at, I believe this was 250 kilometers beneath the surface, something like that. And what he's doing, there's a slab, there's a ocean slab which is diving underneath North America. And so he's looking at where in his simulation that slab is located on that sphere. So basically it's dived, it has dived underneath North America, and here's where the slab is located in his simulation. Seismic tomography was developed later. It was developed about a decade after he began this work. Seismic tomography was this amazing process where scientists at one location with a computer take seismic information from seismometers all around the world, collect the information, and watch how seismic waves went through the mantle. And in that process, they begin to get an idea where in the mantle there's where the waves slow down, for example, where it's warm, where it's cooler. And they began to get a picture of the inside of the mantle, places which are cool. And seismic tomography, which came out years later, located the actual position of the Farallon plate, the plate that is diving underneath North America in the simulation here. The actual position of the plate is here. And the simulation put it here. Whoa. Not only does he have the horizontal motion, but he's got the right vertical position. for these slabs. That's awesome, okay, cool stuff. Maybe even right. as a consequence, you know, I mean, it almost might be. That having been said, when I first saw his subduction zones, like here's North America. He's putting a subduction zone along western North America. There ain't no evidence, put it that way, in the conventional wisdom, if you have convection, if you have subduction, there is evidence, geological evidence of that subduction. But there's no such evidence of that subduction in western North America. So my first response to this crazy idea of having subduction over there is, you gotta be kidding. That can't be true. But Steve Austin and I spent a decade looking at the rocks out there, and we came to conclude that the best way to understand those rocks is that a continent that had an edge out there, what is now California, wasn't there at the time. California is nothing but a bunch of debris that was torn off the continent and dumped out there. So the original continental edge, so yeah, California is just a bunch of junk. The more or less along the eastern border of California was the old edge of the continent. And at that point, we reconstruct, our understanding of the rocks leads us to a reconstruction of the edge of the continent such as this, and then a collapse of the continental margin there, which is very consistent with the idea of subduction breaking. The plate that was sitting there broke off of the continent and began subducting. That would explain the rocks we see in this area. So I came in here believing there's no evidence for subduction. I'm going to go show them wrong. And alas, we find amazing evidence of an astonishing earthquake that in fact cracked the entire surface of the earth along 50,000 miles and collapsed the margins of all of the continents of the earth. So there's actually physical evidence for him putting this subduction where people wouldn't have expected it. And as a consequence, well, I'm going to skip through this. These are the rocks that formed as a result of that collapse of the margin, including humongous boulders that ended up in that avalanche deposit off the edge of the continent. And the amazing thing is, this is the study area we were at. We find the collapse evidences all around the world on the edge of the continent as it would be constructed at the time of the beginning of the flood. So there seems to be good reason to believe that in fact the edges of the continents of the world collapsed at the beginning of the flood, caused by an earthquake that is very reasonably explained by the ocean crust of the world beginning to subduct underneath the continents, or suddenly subducting, beginning the subduction underneath the continents. Amazing, astonishing, global collapse of continental margins that actually makes sense in the light of this model. That also brings to mind the possibility that the evidence we had for the global collapse here was a diamictite of a particular type, a particular kind of a rock known as diamictite. That's not the only place where we find diamictites. We find it 2 other times, big scale, on in the flood sediments. So this suggests that this accelerated plate tectonics might not only explain the diamictites here, but also explain the diamictites in these other positions. We have sufficient power in this mechanism. With continents moving at such an incredible rate, earthquakes are generated of unimaginable magnitude that it would explain collapses, whole-scale, worldwide collapses of geologic structures and the production of diamictites worldwide. It would also have sufficient power to in fact create deformational waves that go through continents sufficient to brecciate dolomites and carbonates. There is no other mechanism we know that has enough power to actually make breccias of carbonate, but this has sufficient power to do so. In addition, we have the megaseismites that we know of at the top of the column. They're probably throughout the column. We've only begun to look for them and to find them. But again, we have in this accelerated plate tectonics, 3 billion times faster than present tectonics, we have sufficient power in earthquakes to explain the features that we find in the geologic column. In addition, we have some other observations in the geologic column that become explainable for the first time with this kind of a mechanism. We have something called low-angle detachment faults. By these we mean faults that are almost horizontal. I mean, they're less than 2 degrees, 2 degrees slope, and we've got huge rock piles moving along these faults. Something with such a low angle, how do you get something to go down such a low angle when you're talking about a rock, not just a rock, a mountain, hundreds to thousands of feet of rock moving down such a mild slope? It's not going to be doing it by any mechanism we have in the present. But the earthquakes generated by this process would create a continuous vibration which has sufficient energy to actually vibrate rocks down low slopes. And in fact, we've got evidence of detachments that occur very quickly. They're hit by major impulses, and then the rocks hydroplane down these surfaces. It's astonishing stuff, not explainable with conventional motion of rocks, but is fully explainable with this mechanism we're talking about here. So the subduction that is hypothesized in catastrophic plate tectonics, what we came to call CPT, catastrophic plate tectonics, or I wanted to call it catastrotectonics, in fact involves the first of 3 things that are happening simultaneously is rapid subduction. That results in, as we've seen, at least via computer models, continental motion in exactly the right direction, exactly the right relative velocity, and there's further advantages to this. We have in those moving plates that are moving across the surface, pulled by the subducting plates, we have continents now moving horizontally across the surface of the Earth. Those continents can and do collide with other continents. And they collide with a certain momentum, which is a function, of course, of the velocity of the continent times the mass of the continent. So let's consider, for example, India, which left behind Africa on the one side, Australia on another, and Antarctica on another, and screamed to the north and slammed into the southern portion of Asia, took 500 kilometers of Asia and broke it off and pushed it underneath the Asian continent. And then continued smashing into the continent to raise the highest mountain chain in the world, crumpling that continent at the impact. What kind of momentum is necessary to break off 500 kilometers by 1,000 kilometers by 50, what is that, 500,000 square kilometers of rock, 35 kilometers deep. Break off a piece like that and shove it underneath the continent in front of it. And then continue smashing into that continent to raise mountains 26,000 feet above sea level. Now, I know India weighs a lot, but moving at a whopping 10 centimeters per year, it doesn't seem to have enough momentum to do what I just described. However, moving at 10 meters per second, the mass of India has sufficient momentum to in fact raise those kind of mountains. The mountains we see, the fold belts we see in the record, are formed by massive collisions that just simply put, at conventional rates, there is no way the continents have sufficient momentum to raise the mountains like that. But this particular model produces sufficient, gives them sufficient momentum to do that. In addition, that collision is now producing lateral compressional forces that are amazing, okay? It is not burying these rocks to great depth over time, and thus they have time to heat up. It is simply compressing the rocks and putting them under extremely high pressure before they have time to respond with increased heat. Under those circumstances, we're creating high pressure, low temperature minerals that cannot be explained in the conventional model, but are automatically a result of this particular model. We have horizontal compressive forces sufficient to explain high pressure, low temperature minerals, which are only found in the fold belts of the Earth. That's pretty amazing stuff. That is just cool stuff. You don't look like you're amazed, but you ought to be, okay? In addition, and this is again, it probably would be best if I had some sort of visual that would show this. But if you see a car colliding with another car in slow motion, go to those the test dummy things and watch all of that sort of thing, and watch what happens to the metal of the car at the point of collision. It's very interesting. Different regimes in the collision behave differently. Part of the metal bends in a recumbent fold setting. Other portions of the metal break catastrophically and are run over the top, what we would call a thrust fault in geology. And in fact, if you look at a collision between two cars, you have regimes of different types of deformation that reflect the kind of deformation that we see in mountain belts. You don't just have rocks that are folded at the collision of mountains. You have rocks that are folded, and then on the far side of them, you have rocks that break and are thrust over the top of other rocks on the forward end of this collision in exactly the same way we see in collisions. Now, the thing is, collisions are high impulse. They're very high energy over short periods of time, and they produce that kind of a response. And when we do this in the lab, we can create we can reproduce features that we see in the field by taking rocks and smashing them together, pushing them together. And here's a problem. When you move them, when you collide these rocks at that massive speed of 10 centimeters per year, they don't behave that way. They don't break in the way, they don't bend in the way that is actually seen in the field. But if you do it at high velocity, or high momentum especially, the rocks deform in the proper way, including the thrust faulting that occurs on the forward side of the collision. We have thrusting where rocks are pushed over the top of other rocks at extremely low angles, really low angles. Basically, if you do this slowly, it breaks and turns at a high angle. The faster you go, the more the two things slide over the top of each other at a lower angle. And the low angle thrusting that we see in front of fold belts, and we're almost in there, we're a little bit, in this location in Tennessee, we're a little bit west of the forward end of the collision belt for the Appalachians. They're the last fault is about, I'd say it's probably 50 miles to the east of us, the last thrust fault. So we have evidence of this stuff here in Tennessee. The low angle thrust faulting found in the Alps and found in the Himalayan mountains and here in the Appalachians is explained by rapid motion provided in this model, but not by conventional model. Okay, that's the first thing that's happening. Simultaneously with subduction, we also have something we call mantle-wide flow, which is to say that as the crustal plates are subducting, there's material having to move in the mantle to take its place, to move. It's got to move out of the way so that the crust can come in, and it moves throughout the mantle and arises at another location. And according to John's model, this subduction, this flow goes all the way to the core mantle boundary. Now this is really important as a distinction from the conventional understanding. Because in conventional understanding, when I learned plate tectonics, for example, it was thought that plate tectonics was restricted to the upper 760 kilometers of the Earth's mantle. The reason for that was very obvious, very clear. We had, the earthquakes are places where rocks move against other rocks. We can determine the position of earthquakes not just laterally on the surface, but we can actually determine their depth. If we have enough seismometers we're getting seismic waves from, we can determine the position. We can triangulate the position of the earthquake even vertically in the earth. And we can actually watch the earthquakes underneath the subducting slab. We can see the earthquakes in the earth get deeper and deeper and deeper as the slab gets deeper and deeper and deeper. Not only that, but we have the ability to differentiate between an earthquake that's caused by compressional motion, two rocks moving against one another towards each other, or rocks that are being stretched apart, or rocks that are being moved side by side. These are called earthquake mechanisms, again with multiple seismometers, determining what type of wave. Several types of waves are shot out by the earthquake simultaneously. Some are compressional waves, some are lateral waves, some are surface waves. The multiple waves run at different speeds, will arrive at the seismometers at different times, and when you have enough of these, you can determine, that's a compressional earthquake. You can not only locate its position geographically, latitude, longitude, but its depth and whether it's compressional or extensional. And so we can tell that these are all compressional earthquakes in the slab as it's moving down. And that's fine as long as the slab is, as long as the earthquakes are less than 670 kilometers beneath the Earth's surface. But something happens at 670, because we have no earthquakes beneath 670 kilometers, number one. Number two, the slabs that have earthquakes at 670 kilometers I'm sorry, I said that wrong. The earthquakes that we find inside the slab are extensional earthquakes. The slab is being pulled, it's being stretched into the mantle. And that is true to 100 kilometers, to 200, 300, 400, 500, 600. But at 670 kilometers, all the earthquakes in the entire plate become compressional. And so, no, we don't have any earthquakes deeper than that. So what it appears is the plates are being pulled down, and there's a wall at 670. And they hit the wall, and it compresses the entire plate, and they can't go any further. And that's true of all the modern plates. So it was generally assumed that there's a barrier beyond which subduction cannot occur. So it was thought that the mantle only circulated in that upper 670 kilometers. And that's what I was taught when I went through school, because, I mean, the evidence is obvious. But when John ran his model that moved the continents in the right direction up here, the plates were moving with sufficient momentum that they actually punctured whatever that boundary is. And we know that there is a boundary at 670. That's a place where the density of the Earth is such that the major mineral in the mantle, which is olivine, actually assumes a different configuration and becomes more dense. And so the density of the mantle has a step up. at 670 kilometers. So there is sort of a wall. It's a thicker place, if you wish, at that point in the mantle. But in John's simulation, the plates are moving apparently with sufficient velocity or momentum that they actually puncture right through the 670 barrier, and mantle-wide flow is initiated. Now, when his model was done and this was proposed, this was out of this atmosphere kind of craziness, because it's clear that subduction doesn't go below that point. But his model had mantle-wide flow. And you can see it here again in the same diagram I had before. The arrows indicate that not only do we have the cooling in the subduction zones, but you've got arrows in the entire mantle. It's motion in the entire mantle. The whole mantle is actually overturning in this process. And here you see what's happening. Oh, this is really cool stuff. I'll back that up in case you didn't catch that. But you start with cool stuff at the top, hot stuff at the bottom, and then what happens in time. I've got to back it up one more in order to make it do that. If I can, doesn't get stuck. Oops, back up, there we go. Okay, watch so you've got material sinking into the mantle, hitting the base of the mantle, then moving laterally, and then rising. We haven't got to that. That's the third thing that's happening at the same time. But this is flow in the entire mantle that's occurring as a consequence of his model. Now, at the time that he made this initial, I'm going to say prediction, because his model said that there should be mantle-wide flow, but everyone said, no, it can't be, it can't be. We had no way to test this idea. It was just a crazy idea that seemed to be counter to the evidence that we had. But what began to be developed in the 1990s, late 1980s, John did this stuff initially in the 1980s, and so he made this prediction in the 80s. By 1990, they had developed a method called seismic tomography, which allowed them to look into the mantle, sort of like a sonogram. Like you would take a sonogram to look at a child in the womb or something like that. It's the same kind of idea. It's using earthquake waves to bounce off of things and get a picture. And just like the pictures of babies have gotten a lot better with technology. I remember when we got them when I was younger, when my kids were, it's like, what? That don't look like nothing. That looks like nothing at all. Are you kidding? Boo. Now we got these crazy things that, my word, there's the kid's arm, and they're sucking their thumb, and oh my word, that's amazing. And the same thing happened in looking at the interior of the Earth. Initially, we're getting very fuzzy pictures of just the very shallow portion of the mantle. But as time went on, the technique improved, and we began to see more clearly, more deeply. And it was really fun to watch it during the early 1990s, because they were reaching further and further in, 100 kilometers into the Earth, 200 kilometers, and it was very exciting because they could see the cold material underneath the subduction zones, just where they were supposed to be. Very exciting. They go 200 kilometers, it's still there, good, this is perfect. 300, 400, 500, 600, they're going all the way down, and it's beautiful. The cold stuff goes right down beneath the subduction zones. They go to 700 kilometers, 800 kilometers, and it keeps on going. And all of a sudden, the party kind of settles down a little bit. It's like, well, what's going on? Let's adjust, something must be wrong. But alas, the cold zones went right through the increased viscosity zone and kept on going. Now, it took until late in the 1990s to get all the way to the core mantle boundary, but it was traceable all the way down. Mind-blowing. Okay, now another thought. If, in fact, John's model is correct and reflects something about reality that occurred during the flood, then if these cold slabs are dropping at meters per second, they've got 3,000 kilometers to go to get to the core mantle boundary. It's going to take them a while, okay? Meanwhile, the mantle's really hot. It's going to be melting them. How long is it going to take? Well, 5 to 8 kilometer thick slab will take approximately 10 million years, maybe even as much as 100 million years to melt away. So in a flood model, where it's dropping at meters per second and getting there in a few weeks or months, it hasn't melted away. In fact, it's only 4,500 years ago, so they should still be there, right? So in this model, these cold plates, they're starting out at the temperature of ocean water. Let's say it's close enough to 0 degrees centigrade. They're dropping into the mantle. All the way down to the base has got 3,000 degrees centigrade temperature down there. And you're going to pile these things up. Now, they can't go into the core because the core is iron nickel, much, much denser. So they're just going to pile up down there, theoretically, into a pile of cold stuff. That's 3,000 degree temperature difference than the hot stuff, the normal stuff in the mantle. Now, you might actually be able to tell that. You might be able to discern where that stuff is. So as seismic tomography got further and further down into the mantle, we're beginning to think, hey, they could test another prediction of the model, which is that there's a pile of cold stuff at the base of the mantle that is 3,000 degrees colder than the normal temperature of the core mantle boundary. And here's a picture of the interior of the Earth with cold zones in the Earth, hot zones in the Earth, and then 240 kilometers above the core mantle boundary. We have temperature variations which exceed 3,000 degrees, reported in 1997. There should be no, again, if things are going at normal rates, it's going to take much longer for these plates to get down to the core mantle boundary than it takes for them to melt. So they would be gone. There should be no cold stuff at the core mantle boundary if things go slow. It's only going to be there if things go as fast as this model predicted. And what we have is temperature differences at the core mantle boundary in excess of 3,000 degrees. Amazing prediction. Pretty cool stuff. Again, that might even make it right. I don't know, maybe. Now, setting John Baumgartner's work aside for a moment, in walks D. Russell Humphreys. Because if we have, back to this position, if we have this situation, think of this, the core, let's ignore in a sense the mantle for a moment. Let's think of the outer core of the Earth. It's liquid. The upper boundary of that outer core is this thing that's showing all these temperature differences. So we've got the normal temperature of the outer portion of the outer core would be 3,000 degrees. But alas, all of a sudden one day shows up cold stuff, 3,000 degree temperature cooler. And remember, the outer core has got a viscosity about that of water. So this is kind of analogous to having a pot on your stove that has water-like substance in it, because water couldn't be at these temperatures, but let's assume there's a liquid that can be liquid at these temperatures. You've got a stove, the stove is on at 3,000 degrees, and it's happy there. Now, let us drop an ice cube onto the top of this thing. Just set it on top. That's 3,000 degrees colder than the burner, okay? Or you could put it underneath, either way. Now, what's going to happen under these circumstances? It's kind of like taking a very big pot and having one part of the pot over in an ice bath, and the other part of the pot on a burner of the stove. You know what's going to happen on the burner of the stove, but it turns out the same thing, but much more vigorous, is going to occur with that dual heating cooling situation. It's going to be a very dynamic motion of the water, as basically what it's doing is it's trying to even up the temperatures. It's transporting heat from the hot area to the cold area to heat it up, and it creates vigorous convection. So this is what D. Russell Humphreys is thinking. He was working with John. He's thinking, well, if you had that on the outside of the core, 3,000 degree temperature difference at different places on the outside of the core, that should induce a circulation in the outer core, vigorous circulation in the outer core. And it turns out, because we believe that the Earth's magnetic field is generated by electrons that are running around the outside of that core, it's in the iron nickel, and they're creating the Earth's magnetic field. If, in fact, the core begins to circulate, the outer core begins to circulate in that fashion, it basically carries the magnetic field lines with it, with the material. As the magnetic field lines are being generated through the material's moving, it's changing the Earth's the magnetic field. And any time, by Lenz's law, that you change the magnetic field, you create a counter electric field that produces a magnetic field to counter the difference, how you're changing it. The effect of this, according to Russ's calculations or estimations, is that it generates a reversal of the Earth's magnetic field as perceived at the surface. Actually, as perceived at the surface, he suggested the Earth's magnetic field would seem to drop to 1/10 its previous intensity, and then flip, and then continue to flip, North Pole becoming South Pole, and then South Pole becoming North Pole, and then North Pole becoming South Pole, at a rate that is related to the rate of circulation of convection in the outer core. And so what Russ did was he said, well, okay, he didn't really know how fast the circulation would be generated. But what he did is took a rough count of how many reversals of the Earth's magnetic field we have in the geologic record, divides that into what he thinks the length of the flood is, or was, and he deduces that it seems that in order to explain the number of reversals we have in the record, you'd have to flip the field every 2 weeks. Now, it turns out when he played around with numbers, 2 weeks is entirely reasonable, as the convection that would be generated in this could easily generate a flipping every 2 weeks. Now, hold that thought. The conventional world also has an explanation for the Earth's magnetic field and for the reversals of the Earth's magnetic field. But in Russ's model, he's starting with a magnetic field he thinks was given to the Earth at its creation, basically by electrons spinning around the outer core, and they've been slowing down ever since. They're losing momentum just simply because they're slowing down with friction. And that's consistent with what we observe you've heard Andrew speak about this, that we've been observing the intensity of the Earth's magnetic field measuring it since 1838. And there is a decrease in the intensity of the Earth's magnetic field, seems to have a half-life of about 1,400 years. And that suggests that the Earth's magnetic field can't be very old. It's the same magnetic field that he's working with to develop this idea of the reversals of the Earth's magnetic field. So his magnetic field is one that can't be very old, means the Earth can't be very old, and it allows, because of that, it allows for very rapid reversals of the Earth's magnetic field. Now, the conventional world has also an explanation for the Earth's magnetic field, but it can't be the one that Russ is using, because there wouldn't be a magnetic field after about 10,000 years. But we have evidence of the oldest rocks on the Earth having been formed in the presence of a magnetic field. So the Earth must have had a magnetic field at its beginning, and we all know that it's 4.5 billion years old. So you've got to have a magnetic field that has been maintained somehow for 4.5 billion years. And so they've developed things called dynamo theories, based upon basically the spin of the Earth is driving these things. and it allows the magnetic field of the Earth to persist for billions of years. But here's a side effect, kind of a negative side effect. The same principle that allows the field to persist for long periods of time makes it very sluggish in reversing. That in fact, in order to get it to reverse, they have mechanisms to get it to reverse, it requires at least 1,000 years to reverse. And to reverse back another 1,000 years. So here we have two models for the explanation of the Earth's magnetic field reversals. One that says they're occurring every 2 weeks. In other words, it only takes 7 days a week or 14 days to reverse. The other one says it takes 1,000 years. So there are pretty big differences in, let's say, predictions about the speed that the Earth's field reverses. How do you test it? There is a way to test it. And Russ suggested the way to test it, the way to determine if his theory was right and the other theory was wrong. And here's the idea. Let's say we have a lava flow flows across the surface of the Earth in the presence of the Earth's magnetic field. Let's say at the place that it is occurring, that it is flowing across, the Earth's magnetic field lines point in this direction. In other words, north is in that direction, and it looks like, what, it's about 60 degrees north latitude is where this particular rock is formed. The magnetic minerals that are within the lava will orient themselves in the direction of the Earth's magnetic field because it is a lava. They are free to rotate in whatever direction they want to go, and so they line up in this fashion. Now the lava begins to cool. Cools from the base up and the top down. So that over time you get cooling here, cooling there. That freezes these particular magnetic minerals at the bottom and the top. So if the magnetic field changes, they are stuck in that original orientation. But let's say before the center of this heats up or cools off, that the Earth's magnetic field flips. If it flips at that point, the little guys in the inside, the magnetic minerals in the inside, will now orient with the new magnetic field of the Earth. When the whole thing cools, you'll have this really weird situation where one lava flow has one particular magnetic orientation on the top and the bottom, and has an opposite orientation in the middle. Now, given that we know how fast it takes a lava flow of a particular thickness to cool, we can then determine how fast the flipping must have been for this to occur. Since Russ was believing that the magnetic field flipped in about 2 weeks, he could then work backwards and say, well, if we look for a 1.5 foot thick basalt lava flow, that should cool in just the right amount of time to capture a reversal if the reversal occurred in the middle of the cooling. I mean, you've got to probably have lots of lava flows before you get one that's just at the right time to have the reversal right in the middle of the cooling process. But that was a prediction he made in 1986. And in 1988, two geologists working in Steens Mountain, Oregon, which is a pile of basalt rocks, kilometers of basalt rocks, but most of them lava flows that are about 18 to 24 inches in thickness, discovered a lava flow, one particular unit, that showed this feature. And based upon the thickness of the lava flow, these are unbelievers, they didn't know a thing about Russ's prediction, never heard of it. If they had, they probably would have gone and studied something different. But they knew nothing about this prediction. They studied this, realized that it indicated a very rapid reversal of the Earth's magnetic field. They sent a paper in for publication. The paper was rejected because the ones reviewing the paper, astrophysicists said, or geophysicists said it was absolutely impossible that the Earth's magnetic field could flip that fast. Therefore, this is bunk. Somehow this is wrong. Well, these two guys are field geologists. You have to understand there's a big difference in geology between the field geologists and the armchair geologists. The two don't like each other terribly well. And these two guys responded by, well, I'm going to go out into the field and find and look for more. So they're going to prove them wrong. They went back to Steens Mountain, found another lava flow that showed the same thing. It took them a number of years, but by 1992 they were able to publish their paper arguing that, that the Earth's magnetic field flipped in 14 days, which is somewhat close to 2 weeks. You know, by my calculation, I think that seems yeah, it's kind of close. So they have this caveat in the paper, and you could tell that they had to put it in because of the reviewers. You know, we don't understand how in the world it flipped this fast, but here's the data. I mean, it's the actual physical data that it flipped that fast. Now, this is really powerful. Not only was this a prediction, which was borne out later, but if it's true, it means the other model doesn't work because it requires 1,000 years to reverse the magnetic field. You can't preserve it that way. That means those models don't work. There's no model left for the Earth's magnetic field except the one Russ was using, which requires the Earth's magnetic field to be less than 10,000 years old. Since the oldest rocks on the Earth have evidence of having a magnetic field in existence when they formed, that would mean that the oldest rocks on the Earth are less than 10,000 years old. This means that the Earth is less than 10,000 years old. I mean, that's the logic that you have to come to with this. Really cool stuff. Okay, the third thing that's happening at the same time as subduction and mantle-wide flow is occurring is spreading. This material that comes down in the mantle and rises, hot material rises to the Earth's surface. This is what we call spreading because it gets to the surface and moves away from that spreading position. And here you can see it again on this diagram. You got the subduction in the blue, the arrows indicate the mantle-wide flow, and the red stuff indicates the warming that's occurred by spreading that's occurring at the Earth's surface. And the concept here is we got 1,400 degrees centigrade mantle material coming up and contacting what? We're in the midst of a flood. Water. It hits water, it vaporizes the water, perhaps propelling it hyperballistically up into the atmosphere and entraining water along the way. It rises into the atmosphere, takes the entrained water, which drops immediately out of it. It cools by radiation, and the rest cools by radiation into space, comes down as intense global rain. So we have a possible mechanism. Now the fountains would be along the spreading zones, which is basically a 50,000 mile long line, basically kind of like the threads on a baseball. Twice around the Earth is the total distance of it. So imagine a geyser 60,000 miles wide, high, and 50,000 miles, 60,000 feet high, 50,000 miles long around the Earth, all going off at the same time, dumping rain, water. It's not really rain because it doesn't go up and create clouds and rain down. So it's a completely different kind of a water addition mechanism to the Earth. Another consequence of this is interesting. At the spreading zone, when this stuff is being applied to the plates as they're moving apart, this is hot material that's moving very rapidly away from the center. If at the same time the Earth's magnetic field is flipping every 2 weeks, let's say we have material coming up right now. The Earth's magnetic field has a certain orientation. As long as that stuff is hot, the magnetic minerals line up with the Earth's magnetic field at that time. If you were to run a magnetometer over the surface of it, you would see a slightly stronger magnetic field for the Earth at that point because it would be the normal magnetic field of the Earth plus the magnetic field created by all the magnetic minerals that are in line with it. And so you'd have a stronger magnetic field over that zone. Then as things moved apart, there'd be a point where the Earth's magnetic field flips. And once it flips, then the material that was once in the same direction as the magnetic field of the Earth is now going in the opposite direction. So taking a magnetometer over that, you would see a weaker magnetic field. So you'd expect bands of on parallel ridges, parallel lines along the ridges, you'd find bands of stronger and weaker magnetic field as you go outward. But think now at the same time, let's say we did this slowly. If we did this slowly, it took, let's say, 50,000 years to move out to this point. It takes 1,000 years for the Earth to flip. In 1,000 years, it's going to produce maybe 100 yards of new material. In that 100 yards, it might be a little messy. You know, is it going to be, which orientation is it going to have while it's flipping? So you might have clear positive anomaly here, but probably a 100 meter zone of kind of mixed up rocks, blotchy rocks. Some might be going the right direction, some might not be. And then you'd have another clear zone of reversed or weaker magnetic field. That would be under the normal conventional circumstance. But what if we sped it up to meters per second? When you're doing this, and the thing is flipping every 2 weeks, you know, there's stuff that was produced, let's say, some of it's cool because it's been cooled with the water, but it's been cooled discontinuously. So you would expect what Russ predicted is that there should be a very blotchy magnetic field everywhere. That if you drill down in these rocks over here, you'd find zones or areas which was normal, and then zones where it was reversed, and then zones where it was normal again, because it was going too fast to have a uniform, rather than 100 yards of blotchy, you'd have everything's blotchy, with more normal in the middle there, more counter in the next, but blotchy nonetheless. This was and what we found is that every drill hole that's gone into these rocks show, and they take the magnetic orientation sometimes every 6-8 inches in the drill hole. We find blotchiness on every single drill hole. So in a normal mode, you might expect, what's the probability of hitting one of those blotchy things? It's 100 yards versus 100 kilometers or something like that. It's pretty low probability. But in the creation model, in this accelerated model, you'd expect the blotchiness in every single borehole, and that's what we observe. In addition, it might explain why these patterns aren't pretty, clear zones. They're themselves, even at a large scale, they're blotchy. This might be because of the speed of this whole thing. In addition, this rapid upwelling, this rapid motion of material up into to the surface, could explain things we encounter in the geologic column known as flood basalts. Andrew referred to them a couple of times. These are slits in the Earth's surface, out of which poured unimaginable volumes of magma. Tens of thousands of cubic miles of magma poured out of these things in the matter of days and weeks. Even by conventional study, they realize this. It's phenomenal. It's literally miles deep of lava over hundreds and thousands of square miles poured out in the matter of days or weeks. When we have all this material rising very, very quickly towards the Earth's surface, I think we have a mechanism to explain these large igneous provinces, these flood basalts. And some of these monsters are actually not only produce, well, the flood basalts are only part of the story. There's flood basalts at the source, and then the rocks actually, they create dikes and then sills that reach out 1,000 kilometers in all directions. So here's the idea. You got enough pressure into rocks, you can crack them, right? If you don't have enough pressure to crack them apart, you might have enough pressure to sneak in between the layers and lift the layers. What we have are places where there's enormous flood basalts, and then cracking the rock in all directions away from that point are these dikes that are found, and you can trace them for thousands of kilometers in every direction. And then they get to a point where they're no longer dikes, they turn into sills because they don't have enough energy to actually crack the rocks. They've lost that energy, but this is at 2,000 kilometers away from the source. They have enough energy to lift miles of rock, just not crack miles of rock. We have one of these, for example, camp is centered in what is now West Indies, and it's cracking rocks all the way through the state of Washington, and it's lifting rocks in Alaska. And the evidence is that the same event is cracking rocks through Europe and lifting rocks in Russia. It is cracking rocks through Argentina and lifting rocks in Chile. That's incredible power. And it's not one of these, there's at least a dozen of these at different places in the flood rocks. And this model would give us the energy necessary to explain these features that can't be explained any other way. In addition, we have these kimberlites. We have these rocks that contain diamonds. What are the conditions to make diamonds? I said it before, you need the right pressure. These things are coming from great depth, but we got to get them to the surface very quickly. There's a diamond source in Canada where we got basically a hole in the ground. We got diamonds scattered all over the ground around the hole. And we know, I looked at the paper, it's really cool. You can take out a piece of, take your napkin and figure this out. It's really cool. I said, what would be necessary? They've got the information. How fast the kimberlite came up through the pipe to get to the surface from 10 kilometers depth to the surface, to get there between 5 and 10 hours after production. It came up so fast that it shot right out of the pipe into the atmosphere, exploded under the low pressure of the atmosphere, and rained diamonds over an area tens of miles around the hole. Well, the information is in the paper, and I calculated how fast the stuff would have to be coming out of the pipe. And it's analogous to having a vertical railroad where each railroad car is carrying, so let's take a coal train, which carries 88 tons of coal in each car of the train. And how fast do we have to have the train moving out of this hole to, in fact, account for this? It needs to move at 60 miles an hour vertically, straight up in the air, in order to get enough material out of this hole high enough to explode in the atmosphere and rain down diamonds. Now, not everything explodes out of the surface. Many of them get stopped before they get to the surface. They ram their way up through rocks, but then lose their momentum before they get to the surface, and they leave the diamonds right there in cold rocks. But the kimberlites cannot be formed slowly. They are formed with incredible speed. And again, in this mechanism, in this model, we have the way to explain things like kimberlites. Another side benefit of this is that we perhaps have a way to explain why the world was covered with water. This spreading is changing the Earth from the pre-flood condition, where we had cold continental crust and cold ocean crust. And what we're doing during the flood is we're pulling the crust apart. We're having hot mantle material come into the place of the cold crust that was there. The hot material, because it's hotter, occupies more volume. In the present ocean, hot material sits 1.5 kilometers higher than cold material does in the same ocean. So you're taking let's say you had a full ocean. Now, in time, you're going to replace all the cold crust with hot crust. You're basically going to take the bottom of the ocean and raise it 1.5 kilometers, a mile. You're going to take the bottom of the ocean and raise it up a mile. That's going to push the water out of the oceans. Add to that 5% of the, on the average, of the mantle magma is water by volume. Add some juvenile water that hasn't been on the surface of the earth before, and in the fact that the oceans occupy 70% of the surface area of the earth, we could easily raise ocean 1 mile over the continents. So we have a continent covering mechanism, a way to cover the continents with water. Here is John's simulation of sea level. There's can't see it here, but there is a purple line that indicates the initial sea level, 20 days into the flood sea level. 40 days into the flood, here's the sea level, here's the beach along the continents. You probably can't see it where you're at, but it's moving in from the ocean by 60 days. That's as far as he gets in his model. He actually brings the sea level up to the mountains, up to the high points, the places that are rising because of their heat. Also, we have reason to believe then, basically this comes from physical data, that there are currents over the continents. John's modeling also produces currents, but doesn't move them in the right direction, so that's probably a bunch of gump. But anyway, again, it's that comparison to the physical data and the real data. But we have evidence that this water covered entire continents and was apparently, for one reason or another, moving over the continents, which is consistent, by the way, with the moon holding the water of the earth and the earth rotating underneath it. That would effectively seem to make the water move from the east to the west across the continents. And that's consistent with the direction that we see in the fossil record. But that allows for the motion, for the deposition of sediments over the continents, such as the Sauk sandstone over the continents. It would explain why we have very thick, uniform sedimentary layers over entire continents. It would also, if we had a mechanism for the east-west currents, which I think may have something to do with the moon, then we can move our sediment from long distances away, and we see this consistently in the geologic column. We've got sediments that we got here. Where do they come from? We go looking for where they came from, because we know what direction they came from by the currents, and we have to go thousands of miles for a possible candidate for where those sediments came from. Sediments are being carried humongous distances, and that would be, again, something that could be explained by this model. It also could explain the abundant, well-preserved fossils that we find in the world. So as powerful as plate tectonics is, and it's awesomely powerful, it is so cool, is such an amazing model to explain the Earth's geology. It explains so much, so many things. Catastrophic plate tectonics, just a slight modification of plate tectonics, just speed it up 3 billion times, and you can not only explain all of these things, but you can explain all the things here in red. Not only do you have magnetic striping you can explain, but the blotchiness of it. Not only can you explain the mantle velocity anomalies, the seismic tomography evidence, but the fact that you have deep mantle velocities anomalies, which you didn't expect in the other model. You can not only explain flood basalts, but kimberlites. You can explain the magnetic field intensities, didn't get into that. The rapid magnetic reversals. You've got mechanisms for thrust faults, detachment faults. You can explain high pressure, low temperature minerals. You can explain some things I didn't get to. See, the talk isn't long enough. And we also have potentially an explanation for other things that are attractive to us as creationists. It explains why the flood came to be, where the waters came from. It may explain what the windows of heaven are, what the fountains of the great deep are. It may ultimately help us explain regional metamorphism and several other things. This is an awesome model for the explanation of the Earth's geology due to the flood. Thank you. Yep. Float your art. Float your boat. Yes, they had some terrible conditions. And I've said this before, but I just have to emphasize this. The more I learn about the flood and the awesomeness, the horribleness of it, the destructiveness of it. There's no conceivable way that and even an ark, the safest place to be is definitely on top of the water. Okay, if you've got, let's say, waves of of a wavelength of a mile, okay, and an amplitude of 500 feet. If you're in the open ocean, it's just, you just go up 500 feet, and you go down 500 feet. You didn't even know anything happened. It's the most wonderful place to be. If you're in the open ocean in tsunamis, you don't even notice it. It's only when tsunamis hit the shallow area over continents that the wave breaks and becomes destructive. So the safest place to be is very definitely on top of the water. Certainly not at the sediment-water interface, where the water is perhaps at this latitude moving at 700 miles an hour across if it's being held. If the hypothesis of the moon holding the water and the earth rotating underneath it is true, then the velocity of the water over the land is 1,000 miles an hour at the equator. Okay, that's at least over shallow areas of the continents. It is not that fast, of course, over the oceans that are deeper, but the safest place to be is definitely on the oceans, but on the tops of the oceans. But these geysers and all these things and possibly asteroids and all this sort of thing, there's no way this ark should have survived, except that we have a God who preserved it through the flood. Again, the chiastic structure of the flood account has a center at God remembered Noah. That seems to be, that is, when you're thinking, oh man, everything's gone, everything's destroyed, and there's no hope. God remembered Noah. Don't forget, people, the purpose of this flood is not just to destroy the evil that was there, it's to preserve humans through it. It's to preserve life through it, which is impossible. In the midst of God's wrath, there are no survivors. Who deserves not to be destroyed by God's wrath? No one. Everyone deserves to be destroyed by God's wrath, and God's wrath is capable of destroying all. It's only in the protective hand of God, in the loving protective hand of God, that we can survive His wrath.